afternoon, ladies and gentlemen. A warm welcome to today's distinguished lecture. My name is Kaspar Althoefer. I am a professor in the Department of Informatics here, and it's my great pleasure today to introduce our speaker, Professor Kaspar Althoefer. So Kaspar has a long association with King's College. He joined King's in 1992, over 20 years ago, and I was a lecturer at King's at the time, and my first memory of Kaspar is of this fresh-faced young man in a ponytail, rollerblading down the Strand and into King's. And I think you will all realize that time has been very kind to Kaspar. He hasn't changed very much in the last 20 years. But one of the things that keeps constantly changing with him is his hairstyles. And I got a very brief collection of Kaspar's various hairdos here. This is only a small snapshot I could gather very quickly. And so he's very innovative when it comes to hairstyles. And then in 1996, he joined King's as a lecturer, and he joined robotics at the time. And we were a team of 2 at the time. And then he and I have been collaborating over a very long time now. So today, Kaspar is a world-leading authority in robotics. He has made pioneering contributions in robot sensing, perception, and intelligence. So it's a really exciting time, I think, to be working in robotics at the moment. He's also leading the Center for Robotics here at King's College at the moment, and he's providing leadership to over 50 robotic researchers. In my biased opinion, this is the strongest robotics group in the country, and one of the strongest in the world, and Kaspar has been one of the chief architects of this success. So today's talk is titled, Robots, Are They Intelligent Yet? And I think it's a very exciting time to be working in robotics today. I think we are on the cusp of something really big. I think it's going to be the next world-changing technology, and to quote Bill Gates, there will be a robot in every home, he said some years ago, in the not-too-distant future. And the question that is raised in the lecture today, robots, are they intelligent yet? I think this is the most fundamental question with which many researchers are addressing around the world. And who better to take us through this talk than Kaspar? Ladies and gentlemen, please join me in warmly welcoming Kaspar Althoefer.
Thank you very much, Kaspar. Yes, who gave you these photos? I didn't think you would show them, but there we are. Yeah, so thank you very much for this introduction. And who could be the better person to introduce me? Thinking that we have been working together for so many years. So you were there 17 years at King's, but actually I've been at King's for 21 years. I did my PhD here, as you said earlier. So thank you very much for this, and also thanks for coming back to join us again at King's to work with us in the robotics group. Good afternoon, everyone. Thank you very much for coming. Especially thanks to those who came from very far away to join me today. It's a very great honor to give this presentation today. So now I have to go out of this presentation, or I don't know, I have to see how I get to mine. Here. Good. Okay, yes, as Kaspar said, so my presentation will be about robots and their intelligence. And so I want to explore this and try to find out how can we define intelligence in robots. What are ways of understanding whether a robot is intelligent? How does it compare to human intelligence? How does it compare to intelligence in animals? So I want to look at different aspects of it and see what different definitions there are, ways found by researchers to actually define this kind of intelligence. So I have a number of here I want to touch upon. So not necessarily all straightly connected to each other. So I want to move around a bit and stretch maybe this idea of robotics intelligence a bit, also to kind of see where I can incorporate my research into this large area of robotics intelligence. And I know that there are many AI researchers here in the audience, and they might have a different view, so I want to present my view on what I see as robotics intelligence and what I have experienced over the last 20 years or so. Let's go in, let's see how it goes. Yep, I knew it would be an experience for me as well. It will be one for you too. I hope for you a pleasant one. In my case, I'm not too sure yet. We have three projectors, and I have two additional laptops operated by my colleagues. Let's see how we can go through this. Anyway, so a kind of definition of what a robot is from 1979, so quite a while ago, and very simple. So really seeing it as a system that can be programmed to carry out certain tasks. Now, Lakmal introduced me earlier, and I remember quite a while ago we were kind of trying to define for ourselves what is a robot, what are the essential bits of a robot. So we came up with this diagram here that brought together the three elements we thought are most important for a robot. So on the one hand, the sensing, sensors that we need to acquire information from the environment. And on the other hand, actuators or motors, so that the system can do something in the environment or something even with the environment. And obviously in between, some kind of intelligence, some kind of reasoning to have a complete robotic system. So very much in line with the idea of embodiment, and I will talk a bit more about this in a minute. But first I want to step away from this a bit and look at science fiction, science versus fiction. Fiction has it easy. Fiction can dream, fiction can look into the future, fiction does not need to explain necessarily. Science needs to prove, needs to find out things and then provide evidence that things are the way that we claim. But science can also learn from fiction, because, for example, we know that the word robot came actually from a playwright. Karl Čapek wrote in 1920 a play on robots and used in there the word robota, and from there we use now the word robot. And it means something like servitude, forced labor, or even drudgery. And from there, from this play, we have started using these words. And there were other writers that are important in this context, and I want to mention Isaac Asimov, who really was a prolific science fiction writer, and particularly interested in robotics, and he actually coined the term robotics. And he also introduced a number of laws, 3 laws, and effectively really exploring the idea of robots and what it would mean if we had intelligent systems in society helping others. And he was very clear about it, that these robots should be helpful to people and should not do any harm. And so he developed, he wrote these books. One of them is I, Robot, and that was also turned into a film. What I found very interesting about it is this kind of mass production of robots. So robots are really produced at the conveyor belt, and then they are sold to people, and they can use them as workers in the home, and they are inside society. They help with mundane tasks. And they do their job, and they kind of cohabit with humanities, until one day things go wrong, and they become suddenly very nasty towards humans, and only one person, Will Smith in this case, can save the world, unless there he is. But let's move on. Another film that really also excited me very much about this idea of robots is artificial intelligence, AI. So it's a movie by Steven Spielberg and was originally kind of conceived by Stanley Kubrick. And in there are robotic devices, robotic systems that look like humans. Again, they live together with humans. They have very many human attributes, and it's actually very difficult to distinguish them from humans, but they have also their limitations. I stay a bit with this movie because I wanted to also introduce this toy that is shown here, so this teddy bear, which kind of seemed actually the most intelligent being in the whole film. And it is very, very nicely animated. It has a really a lifelike feature. It is clever. It can communicate with the humans. And you get the feeling, okay, yeah, that is really a super toy. It can do that. But then if you look behind the scenes, then you can see how it is done, how it is being created. And you can see it is really only a puppet. So only a puppet, yeah, held by strings or levers and moved around and moved in such a clever way that we get the impression it is actually, there's life in there, there is intelligence in there. So that's I think, when we should keep in mind, we can be possibly fooled when we see intelligent systems that we believe that they are of an intelligence that is comparable to human intelligence. Just one more movie I would like to quickly show. I suppose everyone knows about the Terminator movies. So here we have a more negative view of things. Yeah? So these robotic devices kind of reproduce themselves. They take over the world and are against all humanity and try to destroy it. So that is another view. Let's move forward in the presentation. I want to step back a bit and see what kind of other systems have been developed in the past. So according to one timeline, we have here a artificial duck, a robot-like duck that is capable of eating and digesting and even voiding this water. So this is a kind of a first attempt to mechanically have a mechanical machine, or this doll which is capable of actually translating. So that was in the 18th, 19th century. Later I will show another example that goes even further back in time. But let's move forward. So the first actually electromechanical system was developed in 1940. It was a Westinghouse dog, and it had motors built in, combined with mechanical systems, and we could say the first electromechanical robotic system. Then, of course, we had the boom in robotics, the Industrial Revolution, or the second Industrial Revolution, one might say, where robotic devices were introduced into the manufacturing process, and they were very successful. It was a very good marriage because the environment was very straightforward, very planned. So the cars move forward always in a very organized fashion. One knows every time where every object has to be. So the robotic devices can be programmed exactly to move to the right point when required. I'm showing this video that this overlaid on the left and the right to again kind of show that's not the way it is. So these robotic devices, you might want to call them intelligent, that work in the manufacturing industry, but they cannot do that. Here we get the impression that this device, this robot, is actually able to understand the human, is able possibly even to read his mind, and is a painter, painting a car, and then sneakily in the right moment just erasing all traces again. So in order to achieve a video like this, either it has to be fully programmed, step by step, or maybe it's all computer manipulated. So the manufacturing industry is still working according to these earlier principles, like from the 50s and 60s. Everything is planned, and this way one can create, build cars. But moving forward, there was then move towards improving the intelligence of robotic devices. So not only program to them step by step, but to make them more intelligent. So artificial intelligence was introduced, or the idea came up, and the first kind of robotic devices were developed. Here the idea was, you take a computer, and the computer will do all the processing, possibly based on input that comes from sensors or from other sources. And once the processing is done, the command will be sent to the robot. So really,
still really crap.
Really a complete planner, a complete decision-making process, completed and then executed. The problem is, if something goes wrong, if the environment changes, everything has to be planned again. So there was then this new movement, and that was very much kind of supported or initiated by Rodney Brooks, who said, okay, we need now simpler devices, we need robotic devices that have everything on board and that can react to the environment straight away. So instead of complicated models of the world, one should use the world straight away to carry out tasks. So simple robots, that was the idea, simple robots, simple behaviors to be integrated in these devices so that they could react to the environment, sense the environment, and react to the environment, carry tasks out. And that, yeah, is then comes under the heading of embodiment. So trying to link the brain, this artificial brain, very closely with those sensors on the one hand and also the actuators on the other hand. So simple behaviors, and I want to show now a number of examples which will come up in a second, which show this kind of concept. And even in 1950, Alan Turing said, so if you want to create a kind of artificial device that should behave like a human, then you should have the best sensors you can, you should teach it like a child, and then you have the chance to actually develop this kind of intelligence. And Rodney Brooks moves this a bit further and said, okay, so it's not about speaking, but also about acting. So if you have this device that is integrated with all the sensors and actuators, and then you let it loose in the environment, it will be able to learn and to react and do appropriate things in the environment. I link this a bit to the move away by Aristotle from Socrates and Plato. Aristotle said, no, the brain is not separate from the body. These are as a unit. The brain goes together with the body. It's one thing, and we have to see it as a whole to understand intelligence. And you can see now some examples on these screens. So here on your left-hand side, simple behaviors like following your goal and avoiding obstacles actually create quite a complex behavior if put into the environment and if the robots are in connection with others. And on the other side, you saw behaviors like following a parent. So many things can be achieved with very simple behaviors. Also, modern psychology recognizes that the brain is not just functioning by itself, but it is functioning also with respect to what the body is doing. So what your body is carrying out, what muscles are doing, that has feedback, has impact on your brain. And I want to move on now and give more examples that underline the point even further. So, for example, football, robot football, robot soccer. So you can see here these robotic devices, they have simple behaviors built in, behaviors that are appropriate for football, so they have to defend, they have to attack, and they do sometimes very strange things, so now they are just blocking each other, but it is appropriate in the environment because they keep the attacker away from the goal. Sometimes they have strange spinning maneuvers and you think what will just help, but occasionally it happens that the ball comes towards them and is then moved forward into the goal. No goal in this game, unfortunately, but we have another set, so a more modern approach to robo soccer, and here I should start now. Yeah, there we are. So we have slightly advanced robotic devices. they have slightly advanced behaviors, and they have also a leg now that they can use to actually shoot the ball, and very easily can score. I think in the first few sequences, a few goals are achieved very quickly, and you wonder what the goalkeeper is doing, but a bit later I think he wakes up and he's actually quite good in defending, as we can see here. Now, moving forward, what is happening there? So we have now even bipeds, two-legged robots that try to play football, and you wonder what's happening at first to the goalkeeper. Maybe that is part of the strategy, we don't know. But now watch the other player, so he gets confused very easily, but the interesting thing is he always finds the ball again and orientates itself towards the ball and tries again to maneuver the ball into the goal. You can also watch the people in the background, they are very tense now. And as you can see, the player is trying again, and he comes up with a very interesting solution. Okay, so now I have the opportunity also to step back a bit to work that I have done here at King's actually 15 years ago, so this was part of my PhD. So trying to also take this idea further and to program simple behaviors into a manipulator. So instead of, the idea was to move it a bit further and to use fuzzy control or fuzzy logic to describe these behaviors. So very simple behaviors like, if the obstacle is on the right, move to the left. If the obstacle is on the left, move to the right. If the goal is on the right, move to the right. So these kind of behaviors set up in a computer program were used to run this robot. So now I start this, and so you can see. So the idea is for it to move to this position where it is now, is the goal post. So it will move now to the start point, and these black squares are actually the obstacles. So they're virtual obstacles in this case, so I assume I have a sensor that can sense them, and then this behavioral system actually ensures that the robot is always avoiding these obstacles. So it's always trying towards the goal position, but whenever there is an obstacle in the way, it is moving away from it. And I think that was the first time that actually fuzzy logic was used for robot arms in such a way. So I think I show the same video again, maybe I move to the next one. And I hope that is the one I want to show now. So because there are issues, of course, with these very simple behaviors, generally. Because you have only local knowledge, you don't have the global view. And if you had the global view, you could calculate everything and make sure you find a solution and get your robot to the end. But if you use a reactive system, if you have only local knowledge, then you might not get to the final point. And that's the wrong one. I move forward. It's a bit tricky here. No, we don't want that one. Maybe this one here. Try. I don't want to press it too often frantically, because then that's the one. So now I want to reach to the top point. Yeah? You saw it, the robot arms to go to the top. Now it's moving there, so the goal position is trying to get to the goal position. The first link is managing to go there, but the second link now wants to go there, but is at the same time repelled by this obstacle here. So it is kind of frozen in this constant kind of movement, constant trying. So this is one of the disadvantages of these kind of reactive, simple systems, simple intelligence. So they can react quickly, they can move around quickly, can react quickly in the environment, but they might fail at certain points. I take my time, I come back to this picture again. So yeah, so that is kind of our view, this embodied view of the robotic system. And so I want to now look a bit more into the sensing side and also in the acting side. and start with sensing and perception at first. So we have worked quite a bit at King's on this in this area. So we have developed a number of force sensors. So we were interested in sensing pressure and forces. We have applied this to medical robotics quite a bit. As you can see here on your right-hand side, one of these implementations, a prototype there. And as you can see, when the finger applies some force to the tip of the sensor, you see the signal at the end. So these kind of sensing devices are, of course, essential for robotic tools, for robotic systems, and so we have developed quite a number of them that allows us to interact with the physical environment. We have, as I said, developed a number of different sensing systems, and here on the right-hand side is now a sensor which is more complex. It can actually measure forces applied in different directions. And we have also moved this further and implemented this into prototypes. So here in the center you can see a quick overview on how it works. We use fiber optic methods, and the sensors are integrated there, and they allow us to measure forces that are applied at the tip. And we have used this inside of catheters that can be used in medical operations, for example, in a cardiac catheter. And as you can see, the input is given by a force, and we can see the result, the signal on the screen. So this allows us now to have miniaturized sensors that can be integrated in such devices. We have developed cardiac robotic devices that can that effectively are like a catheter and can be inserted in the heart. And we will have later the opportunity to see this also at the stand in more detail. I would like to also mention the Handle project that came just to a conclusion very shortly. In there, we at King's we were very much involved in developing sensing and perception, but it was a multi-partner project, and the idea was to develop articulated hands, so very much based on the shadow hand, and it's nice that Nick Singer is here today from Shadow, and so we have integrated in there sensing devices to equip then this robotic hand with a sense of touch in order for it to grasp and handle delicate objects as required. This was combined with an approach to actually sense the wider environment. We have used a Kinect in this case to actually identify obstacles and objects in the environment, so that this robotic hand then can go in this environment, recognizes the objects and knows where to grasp. And then once the grasping is happening, we can switch over to our tactile sensors and allow the object to be handled in an appropriate way. And that brings me now over to intelligent mechanisms. So I looked at the sensing and perception side. I move over to mechanisms. So these are these things that are attached to the robot, the legs, if you want, or the hands, to operate in different environments. So I have looked at a number of points there: locomotion, articulated hands, and work very much happening here at King's, metamorphism. I would like to mention this context as well. But at first, looking at some walk. So we have here the Honda system, which was introduced quite a while ago, and although it does the job quite good, it needs to be on fairly kind of flat ground, and it's not so happy with stairs, for example. But on the other hand, we have here a more modern system on the other side. So that is the Boston Dynamics. This fits. So here we have a system that is dynamically very stable. It can very nicely interact with the environment, automatically adapt to the environment, and even manage to climb stairs very nicely. So always these robots are on a harness, but usually this harness is only there to hold it if it should fall. They can stand by themselves and can operate in rough environment. So quite an improvement, and you can see here now on your left-hand side the European answer to the to systems that have been developed in the States. On the other side here by Boston Dynamics, and you can see how stable they are dynamically. You can even pick them, and they might even walk over ice, and still they can catch their step again and very easily come up again, even if it's really very difficult to get a hold. So quite an advancement and quite some intelligence in this mechanism and the whole control architecture to keep the system going and be able to adapt to environments that can be extremely harsh. I think another nice example for an intelligent mechanism, and that is a system that I saw for the first time around 10 years ago. So the video on the left is a video I've taken at a conference. I think it was in Lausanne, if I'm not mistaken. And so this is now a wheeled robot, but it's not just wheels attached to the platform. As you can see now, the robot will be actually able to climb steps that are bigger than, higher than it is itself. Okay, so the video stopped at this point. So maybe we can video. So there's a good example now. So the system can actually fold around the steps, so in an intelligent way overcome the steps, and the operator is just using a joystick to move it forward, but the operator does not need to care about adjusting the legs. That will happen automatically. It's a pity that this one doesn't come. No, it doesn't matter. Let's hope the next video comes, because that is now work done by my colleague Professor Jandai. So he's working also on very intelligent mechanisms. One of them is the metamorphic hand he has created, and it can operate more or less like a human hand, but in addition it can fold, so it can be moved into other states or into other configurations, and could be, for example, used in a medical context where you maybe want to fold a hand, insert it into a patient, unfold it again, and then carry out the required operation. And that is another nice example for reconfiguration. So a robot that can change its shape, can reconfigure itself into different types of robots. And as you can see, from something that was some kind of strange robot, it turns into a snake, and it can then move in a certain way. It might change itself back into another robot and even walk around. So that is a reconfiguration in robots. I want to move to the next one here, and I'm not too sure whether it is exactly the right place to show this, because here we look at the aspect of replication and self-replication. So in a way, a very intelligent mechanism that is capable of creating itself again. So we have on the right-hand side a machine, a rapid prototyping machine, that is actually printing parts that can be used again for a new rapid prototyping machine. And similarly, on the left-hand side, you have a robot that is actually creating a tool by itself. Again, using a rapid prototyping approach, it is creating a small spoon and can then use the spoon, attach the spoon to the end bit, and actually move around, as you will see in a minute, and carry things from one point to another. So it's capable of extending itself. So the interesting thing is to explore the idea of robots that can either extend themselves or even replicate themselves and reproduce themselves if you want. So as you can see here, the robot is now picking the water from one side and bringing it to the other side. It has created a tool by itself. And we are working also at the concept here at King's, and you will hopefully also later have the opportunity to have a look at our rapid prototyping machine. Now, another example for an intelligent mechanism Possibly not the right place here because it's something that comes from nature. So it's a fish. Actually, it's a dead fish. A dead fish lying in water. So why I'm presenting that here? Well, you will see in a minute, because this fish is constructed in such a way that the moment water flows, it starts swimming. So it is shaped in a way that it can harness energy from the water flow, and is actually flowing, swimming against the stream. So it's a fantastic mechanism that is built into most fish, and they can make use of that also during their life. But it means that they need only very little energy to actually swim through water or swim against the flow of water. And that gives me now the opportunity to move to my next section, the inspiration from biology. So that is another way of improving the intelligence in robotic systems, to study biology, to study animals, to get ideas from nature and to incorporate them into robotic devices. So a good example are snake-like robots, and here are two examples now. On your right-hand side you have the Tokyo Institute of Technology with their snake-like robot that can move over ground, and a Carnegie Mellon on the left-hand side that can move over ground and can also climb up trees. The one of Tokyo Tech can also even move underwater. So taking the ideas of snakes, their type of locomotion, and trying to recreate them in an artificial system. Another good example where biological inspiration has been taken is this kind of gecko here that has been developed based on the way geckos make use of their fingertips, so to speak, to attach themselves to surfaces and to be capable of crawling up walls. And not only to take the ideas on how the paws are built, but also to study the behavior, the motion behavior, and incorporate this into the robotic device to create a device that is successful, that is capable of climbing up walls, as we can see in these two examples. Okay, now moving on to so now I don't do anything, we just look here left and right. And so we see some algae there in the middle of the screen. Can we see anything else? Can you see any animal apart from the fish that go around? Can you see anything here? Okay, so now I can press the screen here in the center, and it's just very fascinating because suddenly you see something appearing there. So it's an octopus that has camouflaged itself and has been hiding there, virtually undetectable, and a very interesting creature. Many things we can learn from that. One has to keep in mind it is an animal that has no skeleton, so it's a totally flexible, soft device. So if we could now create robotic devices based on these principles, that would be very interesting. And that is something that is currently happening. We are collaborating with researchers from, among others, from PISA. SSSA is the group there, and they have studied the octopus in all detail and have created devices that are taking inspiration, so flexible, soft devices. And are these videos running? They come in a minute. Okay, so maybe I will press the next button. And then we see it all together. So I have created a whole octopus that can be seen here in the middle, and it has now different types of octopus legs attached to it, not real octopus legs, but artificial ones, taking inspiration. And we can see here also some solutions on either side. Different types of arms that are tested out, and they have a number of advantages. They are now very flexible, so they could be used in contact with humans very easily. There is no risk of injury, but then on the other hand they can stiffen the requirement required. So we are making use of these ideas, and I will speak later about it, in the context actually of medical robotics. I want to give some more examples here. So here's the elephant trunk as a starting point, and so we have here on the right hand side results from the company Festo, who have developed this elephant trunk-like robot. And on the other side you see the OCT-arm, that is a robotic device, a mobile platform equipped with a trunk, and this trunk can then be used to grasp things or to explore the environment. I'm not talking too much today about vehicles that go in the air, but I want to give one example here. It looks very impressive, I think. It looks very much like a bird, but it's not a bird. It's actually a robotic device. So this is a device developed by the company Festo. They have studied the bird, studied the behavior of a bird in air, and have tried to incorporate the main features into their robotic device, which can be used now as a reconnaissance robot, for example. Okay, so with the embodiment, the idea of embodiment, simple systems were created that were operating maybe also in simple environments. So you had sensors that sensed something, and then some reaction was required. However, if we go a step further and try now to bring a human in contact with a robot in contact with a human, then maybe things become more complicated. So the idea now of creating robotic devices that can operate together with humans in a reasonable way is another interesting research area, and of course has many challenges. So I start back at kind of a few years back, the beginnings. That is one on the left-hand side. So a simple robot that had some capability of communicating with humans. It could be used in museums to guide people from one place to another. On the right-hand side you see a more modern version. And the idea is for the human to, for example, type questions in, and then for the robot to respond and guide into the right direction. And there have been a number of developments, and so this is a kind of an earlier system which I saw, I think it was also 2002, and I took a video of it. So here the idea is for the robot to somehow interact and to respond to the person, but very simple, yeah? So it's not clear where the system is looking to. So there have been quite some advances over time. I want to talk about a few that have been developed. So maybe at first on the left-hand side is Inca. So this is our robot here at King's. So that's the King's receptionist. And Inca is female, so I can say her in this case. At least that's what the constructor said, the inventor is a female robot. I don't know why they had this idea. But this robot has now cameras built in, so it can recognize the movements of the person, and one can again communicate through a keyboard, and one receives the answer from the system. Here on the right-hand side is Kismet, which is from Massachusetts Institute of Technology, or MIT for short. And so here the idea is to move forward a bit and try to understand the expressions of people and to mimic them in a robotic device. So as you can see, the system is very, can express different emotions, can really follow the person, and you can create this interaction very nicely between the human and the robot. But moving further on that, and maybe I stop the one in the middle for just a second. So we have here on the right hand side we have Einstein, and on the left hand side a fantastic child robot which creates fantastic kind of expressions in its face. So really a move forward to achieve something that becomes more and more human-like, and really capable of showing surprise, fear, joy, sadness, etc. And also, same group, the Hansen Robotics, have developed this robot here, which really looks like a human. And this video you can find on YouTube as well. And you have the impression the robot is really communicating with this person. Now there is really a dialogue, and the reporter is extremely happy from the answers. And it seems really there is a dialogue between the two. Now the question is that intelligence? Or is this just, again, another program sitting inside this robotic device that, true, looks very human, but is this device now really thinking, or are we just getting the impression that this device is thinking like a human? Moving away a bit from it, another type of robots, Sony iBot, and a similar version which is more recent. This one on the left hand side is also 10, 11 years ago, already quite advanced. So a toy robot. A robot, again, for the interaction with a human. The idea is to instill behavior that you can find in dogs. So it's operating, it's kind of behaving in a funny way sometimes. It tries certain things. If it doesn't work, it just lets go. Or it looks in a strange way at the ball, like exploring it. So a number of behaviors integrated there with a reason to create some communication with humans. And I mentioned shortly, this robot is a now robot. Again, a toy robot that can be used for communication with humans. It can dance, it can play music, and different things. But I move forward now to another one, which I find quite interesting. And it has my name, so I really have to mention it. So it's Kaspar from Herefordshire. And so it is a very simple robot, and I understand it is deliberately simple because it is used to help autistic children. And they got confused by complicated kind of emotional expressions in the face. So a simple face which can show and express simple emotions in their faces. And it's also a step further compared to the other robots because it can also react to tactile input. So that the child is allowed to touch it, to play with it, and it will react to it. And so the idea is to use this robot now to really teach the child, to really calm it down, to calm the child down, and to help the child through this kind of process. And when one has a very predictable way of doing it, we can program the robot to react really as needed for a certain situation for the child to learn something. So here's not so much about are we fooled by the intelligence, but it's really using these kind of concepts to improve interaction between robots and humans. Obviously, I have to mention also the Darwin project, where King's is also involved, and is it there somewhere? So the idea is here also to interact with a humanoid, with a human-like robot, and to teach the childlike robot something. As you can see here, the scientist is now trying to tell the robot to actually understand where the objects are and how to grasp them, and to take them in their hands and later actually do the process by itself and repeat the task and possibly adapt to changes in the environment. And it looks very intelligent. It looks like a child is looking at these things and trying to understand it. Is it intelligence? Is the question, of course. Now I want to do a step away from that and quickly look at some other aspects of robots, an area where robots had some impact, robots in the arts, and so that kind of brings me back to something that I experienced as a child. and maybe influenced me also in my choice in later life, who knows. So thanks to my parents, I was exposed to an artist called Jean Tinguely, who was creating crazy machines, machines that kind of moved around in a crazy way, in a very noisy way. My father told me, I had forgotten about that we actually destroyed one of the machines. So we went to this museum. Usually you go to the museum, it's just pictures, it's boring. But suddenly you go there and you can press a button and something is moving, is making a noise. So we did it all the time, pressing the button until it was broken. But nobody complained because at least it was quiet afterwards. Anyway, so these are robotic devices in my eyes, and they're used in art to show movement and also self-destruction. But I was also very pleased to be part of a robotic art exhibition. Rorik Lin from UCL organized and created Fearful Symmetry, which is a huge Delta robot that was mounted in Tate Modern, in the new parts of Tate Modern, and it moved around over the guests, the visitors, and followed them around. So effectively trying to show like a higher intelligence that is hovering over the people, understands them, and follows them around. So I was very happy to be part of this one. And also I would like to highlight this project by one of our current MSc students, who looks at the concept of reconfigurability and applies it to the area of architecture. He's an architect from his first degree, and so he's creating these walls that can actually fold, they can change shape, can be moved into any kind of configuration and even folded away if necessary. And imagine how such walls kind of integrated with motors, so that they could do this automatically, adapt to environments, etc. Obviously, Leonardo da Vinci should be mentioned as well if we talk about arts. And so he was definitely a genius, creating a number of very interesting devices and machines, as we can see here, so like flying machines or military kind of machines. He was also very interested in medicine and really having an impact there as well. And I also found out that he actually also created a robot, so that is now 500 years ago that a robot was created. And this robotic device is shown here, and it has been also rebuilt, now this device based on his drawings, and it could show that it was capable of recreating human-like motions. It could sit up, it could move around, move the arms, move the neck, and even move the jaw. And that is now also my opportunity to move on to the next section, medical robotics. And I also will explain in a minute why I go into medical robotics. But first of all, why is that a link? Well, a company in the States, Intuitive Surgical, also recognized the qualities of Da Vinci, and they called actually their surgical systems the Da Vinci system. So the Da Vinci system is a robotic device, I would say state-of-the-art, really fantastic system, and it is used in minimally invasive surgery or keyhole surgery. Now, why is intelligence important there? Now, if we really look at this carefully, we can see this robotic device is actually tele-operated. So there's somebody with a joystick, a surgeon, moving the different arms of the robot arm and carrying out the operation. So, if you so want, it's again another dumb robot that has been created there. I have to admit they have integrated some nice features. So, for example, they have made the movements very intuitive, so it makes it easier for the surgeon to carry out these kinds of operations. I don't want to linger too much on these images. Just give a quick overview of a number of other robotic devices that have been developed. Here on the left-hand side is Tokyo Tech again, and they have a pneumatic system that allows even to provide some haptic feedback, some force feedback to a surgeon, something that's missing from most other devices developed in other areas, other institutes like DLR, for example. On the right-hand side, we have a system called Raven in the States. The interesting thing there is it is an open source project, so people can provide ideas, can help building the system. Very quickly, similar projects run also in Europe. We are collaborating with a group in Poland, and they have developed a Robin Heart project, or they're working on a Robin Heart project, where they develop a number of different devices, and so they are interested in creating those devices, but at the same time also explore the idea on how to bring back haptic feedback to the user. So for the surgeon, not only to see what they're doing through the cameras, but also to feel what is happening when their devices move inside the body and carry out operations. A few more of those devices I show quickly. Here on the left-hand side, our competitor from Imperial College, developing the eye snake, and on the other side, another competitor is from Carnegie Mellon, another snake-like robot. But I want to now also move to the work that we are doing here at King's. So we are also very interested in this idea of measuring forces, as I said earlier. So we have developed these palpation devices, where the robotic device is palpating the organ, so applying forces to the organ. And at the same time, we measure the indentation. And through this, we can identify the stiffness at various points of the organ. We actually roll over the organs. There's a simulated organ here, not a real one. And then we can get information like this back, where we can see where the organ is more stiff, in which areas. And that gives us an indication on where actually the tumor sits. That will be hopefully helpful for surgeons then to cut out the right pieces and leave the healthy pieces behind. And we have developed this further, and we have developed a number of techniques to improve how the information is fed back to the surgeon. We have worked very much on a concept called pseudo-haptics, where we want to try to trick the human in believing certain things that are actually not happening. So visually representing forces. So and ideally created in such a way that they believe they're feeling the forces even though they see it only, those surgeons who use the systems. But we will have the opportunity, you will have the opportunity later to try it out yourself. So I will move quickly over these slides. And you can tell me whether you can feel something even when you see something. That brings me now to one of the last slides. So StiffLob is a project, a medical robotics project that we have started 1 year ago, and really trying to bring all the things together here. So we are keen to incorporate our sensing and perception know-how. We want to integrate our actuation know-how, and of course want to create intelligent systems, and the main aims are shown here. But one of the really interesting things is that this robotic device is planned to be like an octopus, so like an octopus arm. So not a rigid device, a rigid robot arm like the ones we have seen beforehand at other places, but really, ideally, a robot arm that can be really squeezed, it can be soft, it can be easily kind of inserted into a patient, and then it can stretch out and be rigid to carry out certain operations. So we are very, very keen by this idea of creating this soft robotic device and integrating in there our sensing methods and also a certain intelligence to carry out operations autonomously. So here we have one of our sensors. So there's a stiffness sensor that can be integrated with this kind of robotic soft arm to measure actually how stiff it is at points. Good, and that is kind of the end of the first part of my presentation. And so I've spoken quite a bit about robotics systems, intelligence, sensing, and actuation. And I've also shown quite a bit of the work that we have done here at King's. But I really have to say that is not a one-man job that can be only done with the help of others. And so I want to give my thanks to all my colleagues, past and present members of King's College, who have really helped to move the research forward here and have helped to bring it to that level that we are at. At first I thought I would put a list of names there, but it would have been too big and I would probably have forgotten some names on there. So generally, thanks to those who have contributed. And that includes PhD students, research assistants, research fellows, members of staff, academic, administrative, technical support. Without them it wouldn't work. And of course my thanks go also beyond King's. We had a number of projects, and I mentioned here, I show you on the screen, the different funding bodies, but in particular I would like to highlight the EU projects, which are an ideal opportunity to collaborate with partners within the EU on exciting robotic projects. And here's an overview of the most recent projects I was involved with. And I would like to also thank my family who came here today in great numbers. So thank you very much. It's a bit of a personal note, I know, but thank you very much for your support and also for your patience, especially in the last few days in preparing this presentation. Now, what's next? It's difficult to predict the future, I think, but when I speak about uncertainty, I mean the uncertainty in robotics. So we're looking at very dynamic and uncertain environments, and that will continue to be really an issue people want to look into. So not the structured manufacturing environment where everything is planned, but environments where things are moving, where things are not clear to start with, possibly where we use robots that don't have a complete view of everything, so kind of sensor noise might be in the way, etc. Obviously, soft robots will be something that we are going to look into more and more, and I think there is a general trend to make robots more soft and more compliant, so they can be collaborating more easily with humans, for example. So these are, I think, aspects that will be at the forefront of research and science, and we will try to move to more adaptable systems, intelligent perception systems, and of course control needs to be also developed further. So this kind of uncertainty will continue to be an important topic. Another topic is autonomy, so to see whether we can create devices that become more autonomous, more self-reliant, can carry out tasks without too much human intervention. So development of artificial cognition through learning. Brain modeling could be also interesting, and using maybe also inspiration from nature. But also complex planning problems will be something that will be further kind of explored in this context. And I think we will move towards more extended application. We will extend the application as we have. We will find new application areas. So I gave some examples. Care for the elderly and disabled, factory of the future. So maybe have more intelligent robotic devices to improve the manufacturing process. But anyway, one of the questions I was kind of pondering about is, are these devices, are these humans, not the humans, the robots, are they really becoming like humans? Is there really in their intelligence that is comparable to human intelligence? And I suppose that there is a development of intelligence. These systems are improving and moving forward. But I think, personally, we are still very far away from machines that can work on the same level like us humans. And And in this context, I just put these two slides up on your left and on your right. So I was informed by a good colleague of mine, Maria Fox, that there is actually now a center for the study of existential risk in the UK. I think they're based in Cambridge, and they have important people on board. One of them is a co-founder of Skype, and others are professors at universities, and so they probably have some idea of what's happening in the world and have a perspective. So they believe that robotic devices one day will be a threat to humanity. So a bit like the Terminator style kind of thing which I have shown earlier. Yeah, that is on the one side. On the other side, I put here something that Dagmar mentioned earlier in his speech. So Bill Gates says that in the future, every household will have one robot, and there will be a similar revolution like we had it with computers and the internet. So I'm not necessarily a fan of Bill Gates, and we have suffered a lot today trying to prepare this presentation. And we used Microsoft Windows, yes we did, but we managed in the end. So anyway, I think he has a view for business. So I think we will be moving in this direction. Not too sure about this one on the other side there. Thank you very much.